This is going to be on DC motors, right? DC motors. So we are starting with example 11 from the slides. A shunt motor running at 626 revolutions per minute when taking an armature current of 50 amps from a 4. Wait, no, I'm not supposed to start from this example. There's an example on the top. Sorry. Where is that one too? Or is that the example on the top? No. There's an example on the top at 223. Okay, so from slide 223, right? A 4-pole motor is fed at 440 volts and takes an armature current of 50 amperes. The resistance of the armature circuit is 0.28 ohms. The armature winding is wave connected with 888 conductors, and the useful flux per pole is 0.023 Weber. Calculate the speed. So this is very simple, right? Everything we need has been provided. And so let me just enter my PowerPoint, right? It says we've been given what? Sorry, guys. All right. So we've been given our V. Given V. What? Why is my feeling to draw? Okay, yes. We've been given VA to be 440 volts. Please, there's a class going on behind me, so if you can't hear, just let me know. I'll readjust my position. Okay. I'm even confused. Okay. So we've been given our terminal voltage VA. We've been given our armature current IA to be 50 amps. Our armature resistance RA to be 0.28 ohms, right? And we have Z, which is our number of conductors. Z is being 888 conductors, and flux per pole 5P is 0.023 Weber. Okay. Of course, we've also been given pole pairs to be equal to 2 because it's a 4-pole machine. So it has 2 pole pairs. And since we are using the number of pole pairs for this equation, I'm going to take our A to be 1 because it's a simple wave winding, right? It's a wave connected. So A is equal to 2. Number of poles is equal to 4. 4 divided by 2 is 2. So yeah. And so now for our generator, for our motor, we know that VA is equal to E plus IA RA, right? And we've been given IA, we've been given RA, we've been given VA. So we need to just find E. So with this in mind, our E is going to be VA minus 50. Let me just input the VA straightforward. So VA, we have 440 minus 50 times our R is 0.28, right? So our EMF is going to be 426 volts. Okay. And we know that E is equal to hi guys. Yeah, my internet got disconnected. So please, where did it get to for you guys? So that I just continue from there. Hello, can you guys hear me?
Yeah, we can hear you. Please continue.
So I should continue from.
We can hear.
Okay, so I should just continue from where I'm at right now.
Yes, please.
Okay. Thank you. So times
You are welcome.
number of pole pairs P, all out of 68, right? So if we make NM the subject, we have E by 68 out of Z 5P times P, right? So if we substitute everything that we already have, then we get our NM, our speed, to be 626 RPM. Please, are we okay with this example? All right, so we can continue with the example at slide 252. Right. This one says a shunt motor is running at 626 revs per minute. When taking an armature current of 50 amps from a 440 supply, the armature circuit has a resistance of 0.28. If the flux is suddenly reduced by 5%, find the A maximum value to which the current increases momentarily and the ratio of the corresponding torque to the initial torque. B ultimate steady state value for armature current, assuming the torque due to the load remains unaltered. So one thing that we need to note with this question, right? We know that if we reduce our field, right, we know that omega m is equal to E on K phi, right? So by weakening our field, we should be increasing our speed, right? But then we are making the analysis here with a sudden reduction. So when we are analyzing, right, we are analyzing our current or our changes or the changes in our machine right before it starts to speed up again, right? So we are not going to consider a change in speed because it's a sudden change, right? The flux is suddenly reduced. So upon that sudden reduction, the machine has not begun to speed up yet, right? So our initial our initial EMF is going to be E equal to 440 minus 50 into bracket 0 to 0.28, which is equal to, we've already found this, right? The first example we had the same parameters, so 426 volts, right? So, right after our flux is reduced, we also know that E is equal to K phi omega m, right? So once our flux is reduced, there's going to be a reduction in our E before the speeding up can occur, right? Because if this reduces and this goes up, our E is going to remain constant. But then in that instant, right, the instant reduction, we are going to have a reduction in our E for the time being before the speeding up can now account for it and keep E constant. Okay. So if in that case, that means that once this drops, we are treating this K is a constant, right? And we are treating the omega m2 as a constant because it hasn't started to speed up yet. So speed is the same. So what does that mean? That means that if all other factors here are constant, then the reduction in E is going to depend solely here. So our new E, right? Our new E is going to be equal to 95% of our old E, right? Which is going to give us 404. Guys, please, where was I muted? Please, guys, where was I muted?
Calculation of
Where?
new E.
E new.
At E new.
Yeah.
Yeah.
Okay. So all I was saying there is that our new E, if speed is yet to change, right, and phi and k is already a constant, then our reduction in E is going to be from our reduction in phi. So our new E is just going to be 95% of our old E because we know that phi has reduced by 5%, right? So the new phi is 95% of the old phi. So our new E is going to be 95% of our old E. And with that in mind, our momentary increase in current is just going to be V minus our new E divided by RA, which is this. Are we okay? Guys, please, are we okay? Please, if you don't respond me, when we finish the recording, I won't send the video. Okay. Thank you for the thumbs up. So, the question also says we should find the corresponding torque to the initial torque, right? Okay, so we know that torque TE is equal to K phi IA, right? Okay, so TE2 on TE1, which is the ratio of our new torque to our old torque, right? Is going to be IA2 on IA1 times phi 2 on phi 1, right? So with phi, so we know that with this one, our new IA is 126, our old IA was 50. If our old phi is 100%, right? Then our new phi is going to be 95%. So we are going to have 95 on 100. So this is going to be times 0.95, right? And this is going to give us 2.395. And we know that our motor is going to accelerate, right? Because we've weakened our field, right? So a reduction in IF is going to give us an increase in omega M, right? So it's going to accelerate to make up for that reduction in IF, okay? And then B says ultimate steady state value of the armature current, assuming the torque due to the load remains unaltered. So we talked about the router function. Right? I have the router. So if the torque remains unaltered, then that means that TE2 must be equal to must be equal to TE1, right? And we know that this is IA2 phi 2 is equal to IA1 phi 1. So we have here 0.95 IA2 is equal to 50 times 1, right? So dividing through by 0.95, we get our current IA2 to be equal to 52.6 amps. So what does that mean? That means that after everything settles, right? After right now, our field has been weakened for some time. Our current is now going to come down and settle at 52.6 amperes. Okay. So let's move to example 12. Please, are we okay with example 11? Okay, I'm assuming we are okay with the example 11. Example 12 says a series motor runs from a 400 volts DC supply and has a total armature and series field resistance of 0.2 amps. Variable resistance R is connected in series with the motor for speed adjustment. So we have a first condition here with a given load and R equal to 0. So right now our variable resistance has been set to 0. The current is 25 amps and the speed is this. And on another load with R equal to 2, the current is 20 amps. So we have to calculate the new speed for this condition. Assume that the field flux is proportional to the current. Okay. So I'm going to, all right. So for our first condition, right? For our first condition, we know that the series resistance R is equal to 0, right? For our first condition, right? So at R is equal to 0, we are going to have E is equal to 400 minus 25 into bracket 0.2, right? We are going to have here, our E is going to be 395, okay? And then our second condition says R is equal to 2. So E is equal to 400 minus 20, which is our IA. Hello, please mute yourself. Or let me see. Okay. Thank you very much. Our IA times our RT, right? So we have here 2.2 because 2 is connected in series with the 0.2. So our E2 here is going to be 356 volts, right? And the question has given us our speed for the first condition, right? So here we know we have E2 on E1 is going to be equal to phi 2 and 2, because we know that E is equal to K phi N, right? Or K phi omega. So K is constant, so we can just have here phi 1 and 1. And please, because it's a series motor,
if I'm going to 119.168.1.3, when the packet comes, send it to the router.
Because it's a series motor, our I here is equal to IA and is also equal to IF, right? And we also know here that our phi is as a result of some IF, right? So if IF is equal to IA, then we can take our phi to be as a result of our IA, right? So with that in mind, we can rewrite this as being IA1 and, sorry, I started with 2, IA2 and 2 on IA1 and 1. And we've been given N1, right? So if we want to make N2 the subject, we have here N2 is equal to E2 IA1 and 1 all on E1 IA2, right? So we have IA1. IA1 is 25. IA2 is 20. We've calculated for E2, E1. And the question says our first speed. So the speed for here is at 1000, right? So we just substitute all that in there and we are getting here N2 will be equal to 1128 RPM. Are we fine? I'm going to give you a few seconds to like just take the solution in. Okay. In case you don't understand anything, then just let me know.
Something like, I don't know, something like this.
Okay. So we can move to example 13.
Something like this.
A shunt motor which has a field resistance of 200 ohms and an armature resistance of 0.8 ohms takes 26 amps from a 200 volt supply when running at 500 revolutions per minute on full load. To control the speed, of the motor, a 1.2 ohm resistor is connected in series with the armature. Calculate the speed at which the motor will run when supplying full load torque. Okay. So for example 13, we know we have a shunt motor, right? So
The following information is the following thing we talked about. The last thing they're saying there is that if it is supposed to send the packet quickly, I think it was nanoseconds or something, so implementing it entirely. Right? But if you are able to send a packet, right, or maybe the location for the packet is not known, it means that I cannot forward it by any of my phone.
so this is our shunt motor.
If that's the case,
Right.
I send it back to your routing,
So
and then it's
what are we finding? We are finding speed, right? Okay.
usually your point is supposed to take this from fast part. Right? But once I've sent it,
So if we have RF here
I've sent it to
and some IF here, keep in mind we're giving the value of RF, right? So given the value of RF and V, we know that IF is going to be equal to V on RF, right? So this is 200 on 200. So IF is just 1 amp, right? So this is our I coming from our supply. We have IA here. So KCL, instantly we can tell that our IA, which is our armature current, is equal to our I, our supply current, minus our IF. So IA is going to be 25 amps. Are you okay? Okay.
Come is the exact match because the exact match you use it for. MAC addresses, what MAC addresses are.
So that means that when the series resistance is not connected, our E is going to be, in fact, let me write it there so that I can see. Okay.
Maybe I would say that
So when R is equal to 0, right? Our E is going to be V, which is 200 minus IA 25 RA 0.8. So we have E here being 180 volts, right? So once our armature is connected, our question says, when still supplying full load torque, right? So we are going to take torque to be constant. So if we take torque to be constant and we take our flux to be constant, then that means that as I was saying, if we take torque to be constant and flux to be constant, we know that torque TE is equal to K phi IA, right? So if our torque is constant, flux is constant, this is constant, then IA is also going to be constant, right? So when R is now equal to 1.2, we are going to have our E to be 200 minus our constant IA times 1.2 plus 0.8, which is now going to give us 150 volts. Right.
Hello.
Yes.
You said when the flux is constant, the
Yes.
I is
Yes.
the IH, you said it's also constant.
Yes.
Then the torque would be proportional to
The torque will be proportional to what?
that's what I'm asking.
No, the question says, the first part of the question says, when running on full load, right? So
Okay.
that means that this that we did is on full load, right? And then the question says again, the last part of the question says, calculate the speed at which the motor will run when. So we are still operating at full load, right? At full load, just that a series resistor has been connected. Okay. So if a series
Okay.
resistor has been connected and we are still operating at full load, then that means that our torque remains constant, our field is constant. Then if our torque is constant, our field is constant, our IA is also constant. Right?
Okay.
So we use the same IA to calculate for E when we connect the series resistance because we are still running at full load. Are you okay?
Thank you. Yeah, thank you.
Okay. So if this be the case, let's remember that we're given our speed when our resistor has not been introduced. Our speed is 500 RPM, right? So this is our speed when our resistor has not been introduced. And we are now being asked to find our speed when our resistor has been introduced. So we know that E1 is giving us N1 because phi is constant, right? Then E2 will give us what? E2 N1 on E1. And this is going to give us, substituting everything in, 417 RPM. Are you okay? Are you okay?
Yeah.
All right. So I'm continuing to example 14. So for example 14, we have a shunt machine has armature and field resistances this respectively. When connected to a 460 volt supply and driven as a generator at 600 RPM, it delivers 50 kilowatts. Calculate its speed when running as a motor and taking 50 kilowatts from the same supply. So now we're going to look at it as a generator and as a motor. Okay. Show the direction of rotation of the machine as a generator and as a motor under these conditions. Under these conditions is unchanged. So this question is telling us that the direction as a motor and the direction as a generator is going to be the same. So we should now prove why it will be the same. Okay. So let's pay attention here. I think this question requires a little bit more intuitive thinking, right? So
and the router has maybe 4 output ports. All the 4 are going to different networks, right?
So as a generator, we are going to have the connections like this.
Route aggregation is similar to what our Google like. So maybe output port one has a number of addresses. So like the network, they have a number of addresses, 5, but all of them belong to O.
Driving some load. Oh, my load not here.
So inside the forwarding thing, I'll not write it.
I'm a perfectionist.
The header part. And then we when the router is checking, we check if I
Driving some load here, right? So we will have our IF here, our RF here, our IA here, and our load currents, let's call it IL here, right? With our terminal voltage VA. Okay. So for generator action, our load current IL is going to be equal to our power, 50 kilowatts, divided by our terminal voltage, 460, right? So our load current is going to be 108.69 amps, right? And then our field current IF is going to be VA on RF, right? RF has been given. So VA on RF, we have 460 on 100. So IF is 4.6 amps, right? And then from here, we can tell from KCL that our IA is just our IF plus our IL, right? So IA is equal to IF plus IL. Please keep this relation in mind. We will use it to prove the direction, okay? To prove why the direction remains unchanged, okay? So if that be the case, then our IA is going to be equal to 4.6 plus 100, and okay, so this is going to be 113.29 amps, right? So our EMF here is going to be VA plus IARA, right? VA plus IARA. Our RA has also been given in the question, so we just have our E being 464.53 volts. Okay, so I'm going to move to a new slide for the motor action so that we can have enough space. Okay, so for motor action,
the address I'm sending it to. So come and check in the field. The one it matches with him.
so for motor action, let's redraw our machine, right?
The consistent part, the routing table, I have I have 0, 0, 0, 1, 0. Those cases.
So for motor action, we have some supply driving a current to turn our machine. Oh, I didn't draw the armature.
That example, the destination address. The first one I have 110 101 000.
Right. So this time we have our IF like this, our IE like this. Okay. So we are going to use the same step to find our IL. IL is still going to be power divided by voltage, right? We are going to have the same answer. About some queen.
The second destination address, I have 00011. I come
Right. And then our IF is also going to be the same VF, VA on RF,
So now come and check it. The rest of it is what? 0, 0, 0. And I have 0, 0, 0, 0.
Just that now our IA is going to be IL minus IF. Once again, keep this relation in mind. We are going to use this to show why the direction will remain unchanged, right? So our IA is now going to give us 104.
Yeah, that's why
Point 4. Hey.
once I
104.09.
I'm not saying over the 2. I go back and check the rest of the address. If the rest
Right.
of the address is matched,
So our E for motor action is going to be, once again, we have VA minus IA
like I'm here, I'll see.
RA, right? For the generator, it was plus, for the motor is minus. So we have E to be 455.84 volts, right? And since our machine, everything is constant, right? Even having the same IF, that means that our flux is constant in both machines. We can just relate our speed as E2 on E1 equal to N2 on N1, right? We've already done this, so we are going to making N2 the subject. We have N2 is equal to, you make N2 the subject, you substitute everything in. Our N1 is 600, right? We are going to get 589 RPM for motor action, right? So now let's look at why the speed is going to remain unchanged. Okay, so for generator action, please pay attention here. Okay, speed is not even speed, sorry, direction of speed, not speed, right? Speed direction is unchanged because we know that speed omega m or nm, whichever one you want to use, is E on K phi, right? So phi depends on IF, right? So that means that the direction of our speed is going to depend on the direction of our IF, right? Okay. So if the direction of our speed depends on the direction of our IF, we know that for a generator, IA is equal to IF plus IL, right? So for a generator, IF is equal to IA minus IL, right? Generator. Let's keep this one here. Right. And then for a motor, we know IA is equal to IL minus IF, right? So our IF here is now going to be IL minus IA. So if this be the case, from our question, we can tell that from both situations, right, we are going to have IF to be positive. And we know that when it comes to current, positive and negative show the direction, right? So in both our generator and motor action, we have a positive IF, which is going to mean that we are going to have our speed in the same direction, right? Even though our torque will act in opposite directions, okay? Because our torque depends on our IA, and for one action, we are dealing with negative IA, positive IA, right? So if that be the case, then our torques in generator and motor action will be in opposite direction, but our speed is going to be in the same direction. And the direction of our machine is the direction of the speed. Okay. So this is just to help you understand what is there. For here we have direction of rotation. Since the armature current is positive for one and negative for the other, their corresponding torque should oppose each other. And since the generator torque opposes motion and the motor torque is in motion, the direction of rotation should be the same for the two. So we know that for a motor, right, motor, IA is in motion, right? And then for a generator, IA opposes motion, right? That is why the direction remains unchanged. Okay, very simple. Very simple. I wouldn't be surprised to see a question asking you for something like this because you are going to have to explain yourself, and Dr. Ifa likes it when you have to explain yourself. Okay. Please, I'm continuing to our next example, which will be under a fish. Hey, light out. Hey, wait, my AE is still on. Guys, please, am I still on? Let's go.
Yeah.
Have you had to use my hostel? Ask Lucas. Yes. Like 7:30. 7:38. Okay, guys. I'm continuing.
Akuto,
Father,
please listen to me.
please, what? What did you say?
Hello.
Yes,
Hello.
madam.
Yeah, please, can you go over the last statement you made?
Which last statement did I make? The last statement I made is a light out.
No, concerning the DC machine.
What I said was that I wouldn't be surprised for a question.
Oh no, not that.
Demand you
Like
to
why
explain your direction.
okay, please, why the directions, concerning the directions.
Okay, please. What I said was that. Let me go back. The slide is telling us that DC generator, right? Our torque, the torque we are producing opposes our motion. And then for a motor, our torque is in our motion, right? Are you okay with that?
Please.
Okay. So with that in mind, we know that our torque depends on our IA, right? Our torque depends on our IA, whereas our speed depends on our IF, right?
Yes, please.
So with that in mind, if our IF, with this relation, with the relations we have here, right, we realize that for both cases, we are going to have a positive IF, right? So if we have a positive IF, then that means that both IFs travel in the same direction. So if both IFs travel in the same direction, then simply put, speed will also have the same direction, right? But then the opposition due to torque is because of the nature of our IA, okay? Because in one cycle, we have IA adding to our IF, and then in the other side, we have IA opposing our IF. So that's what we mean by the torque opposes motion in one and aids in motion in the other. So if it does that, then that means that IF is going to be positive in both scenarios, right? because if the torque here was to be greater than our IL, it is going to aid in the motion, and that is going to cause our IF to be negative, right? If our IF is negative and our IF remains positive here, we are going to have different direction of IF, which is going to give us different direction of our speed. Are you fine?
Yes, please.
All right. So now we are going to move to the example under efficiency. Okay. The example 15 under efficiency. Today, I'm going to do what I've done so far. Then I'm going to do one example, the simple example on the status, because I like simple things. And then I'll look at exercise 1 and 2. So hopefully tomorrow morning, tomorrow morning, I'll look at exercise 3, hopefully the grading of status, and some of the examples in slide 1, unit 1. Okay. So yeah, so you let me continue what I'm doing now. All right. So example 15. We have a 100 kilowatt 460. So with this one, I picked out this example because I want to explain something here, right? I pretty much
by dividing this
if you are saying
by this, I think, because the voltage.
Yeah, I'm muting. Hey, say KH.
So it's like
If you are sorry. Okay. So I want to pretty much explain this statement here, right? That's why I picked out this example. Okay. Aside that, it's a pretty straightforward example. Okay. A 100 kilowatt 460 shunt generator was operated as a motor on no load, and its rated voltage and speed. At its rated voltage and speed, the total current was 9.8. So we have here as 9.8 current on no load, right? Including a shunt current. So our field current is 2.7 amperes. The resistance of the armature circuit at normal working temperature is this Ra. Calculate the efficiency of the load. So we know that efficiency is equal to output power on input power, right? So this here is our output power, right? Because this is the power the generator is giving us, okay? So now let's tackle this question, right? So first thing that we want to find is our output current on full load. We've already been given our full load output current, right? So our output current on full load is just power divided by voltage, right? So we have here 100 times, let me even put this here, IL is equal to 100 times 10 to the power 3 out of 460, right? So output power on full load is going to give us 217.5. Okay. All right. And then we are looking for the efficiency in our armature, right? So at full load, we are looking for the efficiency in our armature. So we need to find our armature current at full load, right? And this is a generator. So we know that IA is equal to IL plus IS. I've already demonstrated that in a previous example, right? Our IS, okay. Our IF is the shunt current. So we have this plus 2.7. We are going to get 2. Hey, what happened here? We are going to have 220.2 amps. right? So at full load, copper losses in our armature is going to be copper losses in our armature is going to be IA squared R, right? Copper losses is I squared R losses. So IA squared R, we have our armature resistance given, we have it here. So we just substitute it in. We have 5.325. Hey, please, I'm seeing that the first video is ready. Kilowatts, right? Copper losses at full load in our armature. And the losses in our shunt circuit is going to be, so the losses in our field is just going to be P is equal to VIF, right? VF IF. And VF, we know VF is the same as our terminal voltage, right? Shunt generator. VF voltage in our field is the same as our terminal voltage. So we are going to have here 2.7, which is our shunt field current, times our terminal voltage 460. We have losses in our shunt circuit. So this is pretty much core losses in our shunt circuit, right? 1242 kilowatts. Okay. And then we are going to look at our armature core losses, right? On full load, on no load, we don't have armature copper losses. Okay. We don't have armature copper losses on no load. So on full load, our armature core losses is going to be our IA on no load. Let's say I'm on full load. I'm so sorry. On no load, our armature core losses is going to be our IA on no load.
Before this one comes. It's not necessarily reset. It's just down to look for
times our V, right? And our IA on no load is still going to be our no load current minus our field current, right? So IA on no load is going to be no load current 9 point.
And those two have to finish doing to get out this here before I can send it.
9.8 minus 2.7.
I don't know the speech.
You have to check by memory. To check by memory is when a packet arrives at the input port, it is temporarily stored in the memory.
So our no load armature current will be 7.1 amp, right? Amps. So no load armature core losses is now going to be 7.1 times 460, which is equal to
copy a packet from memory onto the corresponding
3.265 kilowatts, right? And we know that our input power is equal to our output power plus all our losses, right? So we have losses here, and losses here. So our input power is going to be 109 point 109.832 kilowatts, right? So quite simply, our motor efficiency will now be
This is my bus. And the label I put on the packet was 1. So this will receive, this will receive, this will receive, this will receive.
output on
Check the label.
input.
Say 1. The rest is 1 from the packet. And then put it. So all the output ports will receive it. That's what I mean. I think
Right.
the output ports
So you have efficiency to be 91.05%. Please, I will send you some past questions probably tonight. But please, I'm begging you, this is on record. It's okay, I won't send the question.
Oh, you can send. You can send.
Charlie, I know they trust you people. So, plan a frame.
has a power plan A. Like, so if I'm sending from
Please, I'm continuing. So this will
from down,
it's the
if I'm sending from 1 to 1, it's content from 1.
guys, can you still hear me? I had a phone call. I don't know if it interrupted my internet.
Yeah.
Hello.
You can hear you.
Okay. Okay. Thank you. So I'm going to take this easy example, right? Because I like easy things. And then I'll take the hard one tomorrow. So a 240 volt DC shunt motor has a full load speed of 750 revolutions per minute and a full load armature current of 20 amps. The armature resistance is 1 ohm. The maximum armature current during the starting period is 30 amps. Calculate the total resistance of the starter. Okay. So I think I skipped one free page, so I'm just going to write it here so that you know the example I'm dealing with. Example 16 is
the speed of the fabric is faster than the speed of the
we know that
output port.
at start, right,
The speed of
back
the
EMF E is equal to 0. So V is equal to IA RT, right? Where RT is equal to our armature resistance plus any series resistance we add to limit the armature current, right? So we know what we want our IA to be limited to, right? So then our RT, which is RA plus RS, is going to be equal to V on IA, right? So RS is going to be 240 on 30 minus 1, which is going to give us 7 ohms. So how do we call it? The starting or the series resistor or the series resistance required to limit our armature current to 30 ohms is 7. I said 30 ohms, 30 amps is 7 ohms, right? If this does not exist, we are going to have a starting current of 240 out of 1, right? And our IA is going to be 240 amps, which is far greater than the 30 amps we want to limit it to. You understand? Okay. This is a very easy example, so I'm not even going to spend much time there. But please.
Yeah, like if you go
But please, how do we call it?
the rate at which VIP is giving
you will address that one too later. Okay. So please, when I finish solving the examples, let me know that I said I'll address a few things, or else I'll forget. And if I forget, I won't tell you again. Yeah, I mean, I reach. So if you give me the bookend. So now let's look at exercise 1. Yeah.
Oh, Charlie.
Let's look at exercise 1, which I solved in class, but I don't know. Some people said I should solve again. Is it that you don't come to class? I feel like Dr. Ifa. Is it that you don't come to class? Hey, yesterday we had 99 people. Today we have 66. You think I'll send the recording? Okay. So, and please remember to vote for NK. I wanted to wait until we reach 100 people before I say. That will be Andrew Libya. So, vote for NK. This one will come the recording inside. Oh, wow. Yeah, people get things down. All right, so exercise 1. Next time, come to class. Exercise 1, we have a separately excited blah, 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 blah. You can read this on your own, okay? So you know that our VA is equal to 120 volts, right? I'll read the question after I finish writing down these parameters, okay? Don't worry. Our IA is equal to 50 amps, right? Our initial speed N1 is equal to 1045 RPM, right? I'm also going to do omega 1 because I like calculating in radian per second. So omega 1 is just 1045 times 2 pi 60, right? Which is 109.43 radian per second. And our RA is 0.1 ohms. Okay, so let me see. It says a separately excited motor runs at 1045 RPM with a constant field current and an armature current of 50 amps at 120 volts. So that's our terminal voltage. We have our armature current. We have our speed at these conditions. Okay. Keep in mind, it says a constant field current. What does that mean? Constant field current means that we can take phi to be constant, or as Shakalu would say, constant.
So maybe my situation parameter sends 1.
So we can take phi to be constant.
So this one has my situation parameter
And
3.
let's continue. Okay.
So those in
The motor is further loaded
for Salah,
to 95 amps at 120.
there's
So
they do the schedule, but sometimes it's not just
there is also an IA2. Yeah. There is also an IA2
and still 1,000
95
means that
amps,
you see the image I have,
right? Okay.
right? That one looks good.
So
But the thing is,
we are going to be looking for, what did the first question say? What is the speed of the motor at this load? What is the power and torque? Okay, so we are going to look for speed, power, and torque at this load, right? All right. So E V1 is going to be
that's the explanation.
VA minus
The QA inside
IA1 RA, right? So substituting everything in,
that's it, output.
EB1 is going to be 115 volts. Okay.
It's either me or not.
Yes, SK, you've raised your hand. Stephanie, raise you. You can unmute yourself and speak.
So it depends. So maybe
SK.
they've said they've done.
Okay, I'm assuming it's a
This
mistake.
package point that package price.
SK, come again.
Like business, they come to the budget. I really depend on
I
the
said
budget.
it was a mistake. I don't
Yeah.
have a question.
Oh, okay. Oh, okay. Okay. So please, are we okay with this?
That's what I was looking for.
Just substitute everything in here and you get it right. And then EB2, we know our terminal voltage is the same. Our armature current changes, and our RA is also the same. So we are going to get 110.5 volts for here, right? So at a constant phi, we know that E is equal to K phi omega M, right? Or since everything is constant, you can just use the as NM, you get the same thing, right? If this and that are constant, you can relate these two. So EB1, and I hope you can see that he likes these EB1 and M1 questions a lot. So know that some will come in your end of sem exams. Find a new speed. Yeah, it will come. So EB2 is going to be EB2, sorry, N2, sorry. N2 is going to be EB2 N1 all on EB1, right? So substituting everything back in again, we are going to get our our N2 to be 1004.1 RPM, right? All right. So now let's look for power. We know that at electromechanical conversion, mechanical power is equal to electric power, right? So looking for the power at this load is just EB2 by IA2. We found EB2. We were given IA2. PMEC is going to be 10.5 kilowatts, right? And we know that CE omega CE omega M is equal to P mechanical, right? But with this one, please change your speed to radian per second. We know that omega M is equal to N, or omega M2 is equal to N2 times 2 pi on 60. Please change it to radian per second or this won't work. So we have TE is going to be our mechanical power on our speed in radian per second. So we are going to have 99.9 Newton meter as our torque at this load. So we found power at this load, torque at this load, and speed at this load. Okay. So moving on, the next part of so 2 says if the armature voltage is now increased to 180 and the load torque remains the same, what is the new speed of the machine? The load torque remains the same. All this is trying to tell us is that we are still operating at constant flux, right? So if you tell us that the load torque remains the same, then if TE is constant, phi is constant, which was already been said, then that means that our IA is also going to be constant, right? So the only thing changing now is our EB, right? And it says,
So it was
what is the new speed?
why.
So to find the speed, we need to calculate for EB. Calvin, what you want? So our EB at this new voltage is going to be
So
VA2, which was
that color is +1.
giving us
Bucket 1 arrived.
180 volts
Bucket 2 and bucket 3 arrived before I was done.
minus IA2
Because I'm doing out of it.
RA,
When I was
right?
I saw it +1.
So substituting everything in, we are going to have EB at this voltage to be 170.5 volts, right? So now we can go back and we know that EB is equal to K phi
What's given? That's the last thing.
omega, right? So to get this,
Input what's given.
we need to find the value of our K phi, which is at this point so far has been constant throughout because our phi has been constant, right? So we can use any of our EBs and our speed to determine K phi, right? So I'm going to use EB1 and our original speed to determine K phi, right? So our EB1, so our constant K phi is going to be equal to our EB1, which was 115, divided by our speed in radian per second at that voltage, 109.43. So our K phi is going to be
The certain fabric is slower than the input.
1.05, right? So we can substitute, we can then substitute 1.05 here. We are going to get omega is equal to
Yeah.
EB on K phi. So we have here 170.5 on 1.05. This is going to give us our speed at this voltage to be 1550 RPM.
The orange packet.
All right. All right.
So you see.
So the next question says the field current is reduced by 25%. What will the armature current and speed of the motor be for the same torque and armature voltage? Okay. So torque remains the same, but phi changes, right? So what does that mean? That means that our IA is going to change, right? So we need to find our new IA, use that IA to find our EB at this reduced flux, and then use that EB to find our speed, right? So we know that our K is constant, right? So K phi nu is going to be 0.75, 75% of K phi old, right? Because any change in phi will affect K phi. So with that in mind, we have
If I do your front, you can't even do where you are doing. The space there, like there's nothing there. So
K phi nu is going to be 0.75
I finish.
of 1.05, right? This is going to give us 0.7875 as our new K phi. And we know that torque TE is equal to K phi IA, right? And we know that our torque is constant. Our phi has changed. So for this same torque of 99.9, what is our IA going to be, right? So TE is equal to 99.9, right? So IA is going to be 99.9 out of 0.75. 0.7875, which is going to give us a new armature current 126.86 amps. Okay, so 126.86 amps. Now we can bring it back. We have EB is equal to VA minus 126.86, oh, 86, okay, into bracket RA. Keep in mind, we are still using VA to be 180 volts, right? So substituting everything here, we are going to get EB to be 167.3, right? And we know that our speed omega is equal to EB on K5. We found our new K5, so we have 167.3 on 0.7875. This is going to give us 212.4 radians per second as our speed when our flux is reduced. Are we fine? That's the last question before I go to example 3.
What we talked about, the routing protocol is supposed to determine an end-to-end path.
Yes, Isabella, do you have a question?
Yeah, I mean, it's good in it.
Okay, so I'm assuming no one has a question. So I will continue with the exercise 2. Then we call it a day. Yes.
This guy say call me. Telephone number.
Who?
George.
Okay. Okay.
Say some 0507.
Yeah, I have it. I have it. So
So I said the routing. I'll go ahead and the routing process.
exercise 2.
Supposed to determine the end-to-end path. And there are multiple paths. We're supposed to determine a good path or the best path.
Please, someone should read the question for me. I'm feeling myself.
Or fastest or least congested. I think you're missing. You're missing
If they don't read, I won't continue.
some vector question.
Please, someone should read the question for me.
Come me down. Come me down. Come me down, Kivan.
We just come there, I can't read it.
Yeah, come read.
Your intra domain question. No, we'll answer it. Well, I'll answer it. And then I'll answer you for the question.
Hello.
Hello.
Yeah, read.
Yes.
Exercise
The
2.
amateur winding.
The armature winding of a 4-pole permanent magnet excited DC machine is lap wound in 46 slots with 18 conductor space slots. The permanent magnet field opposes field poles span 70% of the pole pitch, and the peak air gap flux density is 0.7 Tesla. The machine has an air gap diameter of 15 centimeters and a core axial length of 25 centimeters.
All right, thanks.
What?
So,
Sure.
thank you very much. If the
God bless
armature is designed to carry a continuous current of 100 amps, what is the maximum electromagnetic torque developed by the machine? Okay, so let's get into this. All right, so I would like to write down a few of the parameters before I get into this question. Okay, so we know that the machine has 4 poles, right? So number of pole pairs is 2, right? And is a lap wound, right? Lap wound. So A is equal to P, right? we have 46 slots. 46 slots and 18 conductors per slot, right? So this means that we are going to have number of conductors, capital Z, to be 18 times 46, which is going to give us 828 conductors, right? And then we know that our peak flux density is 0.7, right? And our field pole span 70% of our pole pitch. So we have lambda F on lambda P to be 0.7, right? And then we've been given a diameter B as 0.15 meters and length L as 0.25 meters. And we have an armature current IA equal to 100 amps, right? So now with this, we are going to solve our question. Okay. So we have here our average flux, right? We've been given our peak flux, right? But we want the flux that is going to span from pole to pole. So that's going to be our average flux. Okay. So our average flux, B average, is equal to lambda F on lambda P. So our average flux is essentially the effective flux being felt by our poles, right? So the flux under each pole is going to be this times pole peak, right? Flux peak, flux density peak. So we are going to have here 0.7 times 0.7, 0.49 Tesla, right? Please, okay, right, okay. And we are also going to find our pole pitch, lambda P. Lambda P, which is our pole pitch, is going to be equal to, let me see what this is. Yes. Okay. So our pole pitch, which is essentially the distance, is you, the distance of the pole, which is going to experience the flux, right? It's essentially the area of our air gap. It's yeah. And then one different the area of our air gap pi d on 2p, right? So 2p is equal to 4. So we have here our pole pitch being 0.117. Hey, no, this isn't area, okay? This is just a fixed formula, okay? This is a fixed formula. So keep it in mind. 81 meters. Right? This is the formula for our pole pitch, okay? So all this that we are doing, okay, we are just trying to find flux, right? Flux per pole, phi p, okay? So we are going to use this to find the area per pole, okay? I'm coming, we'll get there. You are going to see what I do real quick. So our area per pole sorry for the background noise. Our area per pool is just the length of our pool, which is our pool arc, which is just lambda f times the length that we're given in the question. And so to find lambda f, we know lambda p, we know lambda f from p, right? So then we can find lambda f. So lambda f is just equal to lambda f on p a. Lambda f on lambda p times lambda p, right? So we are going to have here, this is going to be 0.7 times our pool arc, right? We found lambda p here. We know lambda f from p is equal to 0.7. So our pole arc, lambda f, is going to be 0.082 0.08267 meters, right? So area, pole arc times length. We've also been given our length. Our area per pole is now going to be 0.0206 meters squared, right? And we know that flux phi is equal to P times A. So our effective flux times our area per pole should give us our flux per pole, right? Or our useful flux. And that's going to be 0.0100102 Weber. Right. Okay.
These networks are connected to the router, they are visible in the routing link. So if when you're doing the labs, if you put interface, you give an interface an address, and you give it another.
So we are looking for torque at armature current 100 amps, right? All right. So we know that our torque TE is some constant, let's say KT, times our phi P, which we just found, times IA, right? So bear with me for now. I'll explain why the constant is obtained the way I obtain it after I finish solving this question. Okay, so bear with me for now. Our constant KT is equal to PZ on 2 pi A. Okay, we know A is equal to P, so it's going to cancel out. So we have essentially, let me write it in full for now. 4 times Z 828 out of 2 pi times 4. So our KT constant here is going to be 131.78, right? So bringing that in here, we have our torque to be 131.78 times 0.010102 times our IA, which is 100 amps. So our torque is going to give us 133.1 Newton meters, right? That's it for the first part. Okay. And then our second part. Now let me show you how. Okay. Our second part says calculate the voltage induced in the armature winding when the rotor speed is okay. So we know that Hey, I just realized I was muted. Guys, excuse me for a second. Please, can you tell me when I go muted? Because I just realized I was muted. Before.
Is to know the number of.
Guys, please, when was I muted?
How many votes can I have? Right. When I'm writing,
I'll continue like that too. Are you guys sure you can hear me? Well, okay. So, all I'm
Yes,
trying
we
to
can
say
hear.
is that, okay, so I'm continuing. So, all I'm trying to say is that if this is also some K, phi, NM, right, then we can take all of this as our K, right? And we also know that EB is equal to K, phi, omega M, right? This is the actual equation, right? So to change this to omega M, it will just be times 2 times 60 on 2 pi, right? So this 60 will cancel this 60, making it on 2 pi. That is why for this one, we have it as PZ on 2 pi A. Okay, so it's the same thing, just that we are working with radian per second with torque because we know that we want a very accurate answer. Okay, that's why we assume that our constant to be equal to this. But then all we are doing is that our constant is equal to the PZ on 60A, right? Just that if we change it to omega M, it becomes 2 pi because the 60s cancel out. Okay, so what I'm going to do is that I'm going to take a certain constant Ke so that whichever answer we get for our speed, I can leave in Nm like RPM directly. Okay, so I'm going to calculate a certain constant Pz on 60A, right? Because the speed we're given in the question was given as Nm. So that with this, yes, Pearl, you have a question? Okay, so that with this, I can use the speed directly without changing to omega m, right? But then if I wanted to change the speed to omega m and use, I would have to use this as my constant, okay? So with that in mind, D and P will cancel, right? So for this one, our Z, we are going to have 428 on 60, which is going to give us a constant of 13.8, okay? So now substituting that in, we have EB is equal to 13.8 into brackets 5, 0.010102 times NM. Our NM was given in the question, right? As, where's our NM? Hey. Our NM was, oh. Oh.
What happens if the
Please, I don't know what has happened. It's not my fault. I'm not good with modern technology. So I'm just going to check the speed for my slides on my phone. So, yes, 1,800 RPM, right? So, 1,800 RPM. Hey, am I still connected? Guys, please, am I still connected?
Yeah, you are.
All right. So, this is going to give us an induced EMF of 250.9 volts. Okay. And then
If I lose one,
question 3. I have to read for my phone because my technology is messing up. Question 3 says, if the machine is supplied from a constant DC voltage source 380 volts and the armature resistance RA 0.5 ohms, what is the rotor speed if a load of 20 Newton meter is applied? State any assumptions made. I can't remember the assumption I made when I was solving this question. Okay, so okay. I think I can. Hey, wait. Okay, I think I can remember. Yes. So the assumption being made here is that our flux is kept constant, right? So that means that our TE is equal to KT phi IA, right?
I specify the route to the next page.
So if our flux is being kept constant, then
Even though
our new IA with this new torque is just going to be IA is equal to
if the limit
TE on KT phi, right? So we have here 20 on 131.78, which we found in one of our previous questions, times our phi 0.010102, right? So IA is now going to be, for this torque, IA is going to be 15.03 amps, right? So now we can just find our EB using VA minus IA RA, right? And our VA has been given us 380, right? So we have here 380 minus 15.03. Wait a minute.
if I can get this through out, I also think people will now say that, oh, get to this network through out. That's automatic. I started, I told the router that pass A, get in. If that link is closed, until I tell the router to pass a different location, it cannot get to the network.
Okay. I think I've sorted out my issue. Times.
What's if the route is linked via multiple sources? Each source of routing
Our RA, which is 0.5. Then we are going to get our EB to be 372.485, right? Okay. So then our speed can just be our new EB that we just found out of our constant. Once again, we are using this constant so that we can get directly our speed in RPM. Okay, you can use this constant. You are going to get the speed in radian per second, right? So 2672.5 RPM. Okay, so that's it for example 3. Exercise 2. So we will be continuing tomorrow with exercise 3, the grading of the starters, and hopefully unit 1. Okay. So now what I want to do is I want to give you guys some advice on certain things you should look out for. Okay. So yeah, he said question 1 was going to be from unit 1, right? And he said it's going to be electromechanical conversion and it's going to be electromechanical conversion and magnetism, right? So with the magnetism, because the midterm was asking about permanent magnets, I think it's safe to assume that your end of sem might ask about characteristics of magnetic materials, right? That make them suitable for DC machines. So maybe everything from the BH curve downwards, right? High BR, high AC, good linear characteristics, blah, 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 how Nico this, blah, 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 those things, right? And question 2 is going to, I think, is going to focus on the problem of armature reaction and its solutions, right? So I think, oh,
The previous year, no, the previous year, the only lab question he had them was look back at this. You bring the last, you bring the last.
So I think
10 marks or something.
anything from this slide, right? This slide right here to this slide, okay. And then
Yeah, but I didn't see that thing.
and then I'm thinking question 3 is probably going to focus on why you need to add a starting resistance to mitigate a high starting current, right? Or you could also focus on torque characteristics of DC motors or torque speed characteristics of DC motors, right? So please keep in mind the application of DC series motors and DC shunt motors as well, right? And why DC series motor is used for high starting torque applications. And then for question 4, I think he said it in class. Also, yes, the question 3 calculation part. Please pay very close to attention to the grading of starters question in the slides, okay? And also pay very close attention to n-1 and n. I think n is the number of steps, n-1 is the number of sections. Last year, he gave a question with number of sections, and people didn't read the question. Once they saw number, they just did n-1. But number of sections already is n-1. So pay attention to that example too. And the questions from unit 3, I think the calculation part of the stepper motor is a guarantee. Unit 3, I think is going to be a bonus, right? So the calculation part of the stepper motor is a guarantee: step angle, step response time, resolution, and then I think the unique features of a servo motor. I think he said in class that he would bring questions on that as well. So yeah, please don't take my word to be law. Okay, this is just an opinion. In fact, I should have even stopped the recording because some of you go and say I saw the questions and give them to you. Please, I've never seen questions in my life. So on that note, I will end the meeting and David Osre, fair enough. I will end the meeting and allow you to go and revise, right? So all the best to you guys. I want someone to pray for us. Let me see which part is. Hey, and I almost have to go offline. Please, before you go offline, vote for NP. Oh, I should have said this when it was still 71 participants. Now it's 63. Yes, who has their hands up? You can unmute yourself and ask.
Processes associated with the discovery of parts, various destinations from the MCA. So that's the routing to
We are praying.
Hey, we are praying. Eh? Okay, then pray
Please,
and
I'm
let's
asking
close.
a question.
Yes, please ask your question.
Yes, and please, yesterday when you were solving, I think, is it exercise 3 or so from the second unit?
Oh, leave yesterday's problems in yesterday now. Okay, yeah.
Please. Yeah. So you see that question that he was like from 39 to 45, but then you were like, he meant between. Is it that
Yes.
whenever we see from, we should think of between? Or it's just for
Ho-
that question?
Honestly, I would recommend whenever you see from, think of between. Okay,
Okay.
that's the advice I would give you. But I think the question, even the nature of the question, would allow you to know, right? Because for the nature of that question, it was only going to work with 41 and 43, right? So if the range is very, very small, right? Let's say if it was already 40 to 44, and it said from 40 to 44, with you knowing that it has to be an odd number, then that one you can know that it's from 40 to 44. Because that one, there are only two odd numbers there. You understand? So the nature of the question will also allow you to know.
Okay.
So if the range is very wide, I think it's very safe to assume that it's between, okay. But if the range is very, very close, then you can take it as from. Please, is there any other question? Okay, so please, who
Okay,
was
thank
praying
you.
for us? You're welcome. Pray for us and let's close.
If the network of 5 routers, and pick one router, that router knows that you are the router. And then the cost of the house gets, what is to get